module 2, lecture 2, and the topic that we will discuss today is on ion exchange chemistry. So the concept covered in this lecture will be on ion exchange chemistry. We will talk about that how the ion exchange chemistry works and how the ion exchange process happens, what are the chemical reactions that happens behind it, and what are the different type of parameters that we need to consider so that we can find out that how much percentage of the ions will remain on the resins, how much percentage of the ions will go into the solution. And this also depends upon the selectivity coefficient. So we'll talk about the selectivity coefficient, then we'll talk about the ion exchange regeneration technologies, and we'll talk about the co-current regeneration system and counter-current regeneration systems in the coming slides. So when we talk of the ion exchange chemistry, let us consider a simple equation here, that is R minus A plus, that is here this R minus A plus represents the A plus ions which are present on the resin, whereas Bn plus are the ions which are present in the solution. So when these Bn plus ions are there, so they will try to replace the A plus ions which are present on the resin, and the reaction will happen in such a way that the Bn plus ions will go on to the resin, whereas A plus ions will come into the solution. That's how the ion exchange takes place. So we are talking about the constituents which are present on the resin, that is R minus A plus represents the percentage, or basically we can say the ions which are present, A plus ions which are present on the resin, whereas the solution, the ions only, they represents the ions present in the solution. So here we can see this R minus is the anionic group which is attached to the ion exchange resin, and it represents the resin form. So if we write down the equilibrium expression or equilibrium constant for such a equation, which is again reversible equation as we have discussed earlier also, so we can see that the value of the K, that is the equilibrium constant, where Bn plus is replacing A plus ions, so this can be represented by A plus, which is in the solution, similarly into the Bn plus which is present on the resin, whereas divided by R minus A plus which is there on the resin, and divided by the Bn plus which is again in the solution. This value of the equilibrium constant represents the selectivity coefficient, and these are the concentration of A in the solution, and R minus A plus represents the concentration on the exchange resin. So as we go further, we can write down the removal of sodium and calcium from the water by using a strong acid synthetic cation exchange resin, and the regeneration of the exhausted resins with HCl and NaCl. So we can write down the equation or the reaction which happens when we are having R minus H plus as the resin. So the resin is having H plus ions as the exchange ions, and Na plus is present in the solution. So after the reaction, the R minus Na plus becomes, that is the Na plus is replaces the H plus ions, and H plus ions moves into the solution. So this is the reaction that happens for resin, which is basically a cation exchange resin having H plus as the exchange ions, and the sodium is there in the solution. Similarly, we can write down the another equation where R minus Na plus. So now if this resin, which now becomes R minus Na plus, is now comes in contact with the calcium, so then the equation basically becomes like this, that the calcium ions will replace the sodium ions, and sodium ions will go into the solution. So if we want to regenerate this resin, so we can say that R minus Na plus, we put it in contact with HCl, where basically we are having the HCl maybe having a strong solution of HCl that we prepare. So H plus ions will replace the Na plus ions here, and now our resin becomes R minus H plus. And similarly the NaCl goes into the solution. And similarly, when we are having the resin which is laden with calcium, if we take it into the contact with the brine solution, a concentrated brine solution, so here also this sodium ions will replace the calcium ions, and our resin will now be replaced with sodium ions in place of the calcium ions, and calcium goes into the solution. So that is how the regeneration process takes place. So regeneration process, you can see that instead of the calcium replacing the H plus ions, the reverse is happening. or we can say the sodium ions replacing the H plus ions. The reverse reaction is happening, that is now H plus ions, they are replacing the sodium ions. So this happens when we are having a very high ionic strength, which is basically put onto the resin. So if we are having a very high ionic strength water or solution, for example, we are having concentrated solution of HCl solution, or we are having concentrated solution of brine, so they replaces, generally they replaces the ions which otherwise basically may not be replaced in the dilute solution. So that's why we provide a concentrated solution of brine or concentrated solution of acid, so that the resins can be regenerated. So the equilibrium expressions for these reactions, that is the reactions 1 here and reaction 2, so this can be represented by this equation, that is Na plus is replacing H plus ions. So here we can see that H plus and the Na present on the resin, and similarly R minus H plus, that is present on the resin here, and this Na plus which is present on the solution. Similarly, calcium is replacing the sodium ions, so we can write down the equilibrium expression for this, that is sodium whole square, because you can see that when you balance the equation, so 2 times of Na plus comes into the solution, so Na whole square into R minus calcium, that is calcium present now on the resin, and similarly this is in the solution. Similarly, the sodium present on the resin, so this will again come as square here, that is on the resin, and the calcium which goes into the solution. So these expressions which are there, so they are also known as the selectivity coefficient. So we can see here that there are typical series where basically we can talk about that whether the cations or the anions, they will replace another cations or anions or not. So these series basically you can see that, for example, here you can see that in the monovalent cations, the silver can replace rubidium, rubidium can replace potassium, potassium can replace ammonium ions, ammonium ions can replace sodium ions, sodium ions can replace H plus ions, and H plus ions can replace lithium ions. Similarly, when we talk of divalent ions, so the barium can replace strontium, strontium can replace calcium, calcium can replace copper and cobalt, and then zinc and magnesium. So in this way we can, by seeing these series, the typical series, so we can decide that which ions present in the solution will replace which ions present on the ion exchange resin. So these series, typical series, are generally applicable for dilute solutions. When we are talking of the dilute solutions, so in that case, these series, they hold good. Whereas in the concentrated solution, as we have seen, or the solutions having highest ionic strength, so generally this may not be the same case, because we have seen earlier that in case of regeneration, this is often reversed. Similarly, we can see for the anions, for example, chlorate will replace nitrate, nitrate will replace bromide, bromide will replace chloride, and bicarbonates, and then fluoride and H minus ions. So in this way, we can decide that what type of ions will replace which type of ions which are present. And when we talk of the selectivity coefficients, so these selectivity coefficients, they are generally measured in the laboratory, and they are valid for the conditions in which they are measured. That's why we can say that the whatever the selectivity coefficient values we get, so they are specific to a certain set of conditions. So we can see here that the table 1, which shows that what are the selectivity coefficients for various type of cations here in this case. For example, we can say the lithium is having 1, 1.3, sodium is having 2. So these values basically tells us about the K values which we get basically when we are having different type of reactions that are happening in the ion exchange resins. So these K values will represent what are the selectivity of various ions over the H plus ions. Similarly, we can see the selectivity values or selectivity coefficient values for the anions in the table 2, and we can see that there are different type of values which are given here, and these values may also be used for finding out the K values or for finding out the concentrations of various cations and anions which are present on the resins and what fraction is present in the solution. So affinity of ions can be generalized. For example, we can say that in general, the high valency ions are always preferred over the low valency ions. This performance increases with the decrease in the ionic strength. So as I have already discussed that if we are having a very high ionic strength, so in that case this preference may not hold good. For example, the high valence are preferred over the low valence. So this condition is always applicable when we are having a solution which is having a low ionic strength. In that case, this is applicable. Similarly, if we are having the same valency of ions, so the extent of the exchange will depend upon the hydrated radius. That is, if the lower the hydrated radius, the higher the affinity. And similarly, the increasing atomic number increases the affinity. For example, here the larger hydrated radius, so it increases the swelling of the resin, and that's why it decreases the affinity of the resins for such ions, because the pore sizes decreases as the swelling of the resin increases. So that's why the decreasing hydrated radius will always have a higher affinity towards the ion exchange resin. Similarly, when we are having the high ionic strength, so in that case, our exchange reaction follows no general rule and it's often reversed, as I talked in the first point also. So when we talk of the regeneration of the cation exchange resin or anion exchange resins, so we are having a very high ionic strength with water, and that is basically put onto the resin. So in that case, the ions which are less preferred in the dilute solutions, so they may also replace the ions which are more preferred. For example, the monovalent ions can also replace the divalent ions in that case. So that's why this rule may be reversed in the case of high ionic strength solution which is applied to the resins. Similarly, the degree of cross-linking and size of the hydrated ions may also affect the exchange reactions. For example, if we are having a high degree of cross-linking, so then the ions basically may be too large, so they may not penetrate the matrix of the resin, and that's why the ion exchange process may be hampered, because or the efficiency of the ion exchange may decrease because of the lesser amount of space that is available for the ion to penetrate into the resin and to go inside the resin, and there may be other sites also which may not be accessible in that case. And similarly, the size of the hydrated ions may also impact, that is, it may increase the swelling, and because of which the size also reduces. If we are having a very high affinity resin, for example, when we talk of the strong resins, strong acid resins or strong base resins, so in that case we can find certain properties. For example, we can have a sharp breakthrough curve. So what does this means? For example, let's say we are having a resin which is having a very high affinity of certain ions. So what will happen that initially the water which contains a certain targeted ions, so it will slowly and slowly fill or replace the ions which are there on the resins, and until and unless all the total exchange capacity of the resin is utilized, then suddenly you will find that cations or anions of interest, they start coming out of the solution. So you will find the breakthrough curve just like this, that is suddenly a sharp rise of calcium or magnesium or whatever the ions of interest, so which are basically being removed by the resin, so they start eluting out suddenly sharply, right? So the breakthrough curve may not be slowly and slowly rising, that as happens when the affinity of the resin may be low, right? So when we talk of the weak exchange resin, so in that case, you will find such type of breakthrough curve. But in case of the strong basic or strong acid resins, so we find that the breakthrough curve may become like this. That suddenly the concentration start increasing in the effluent. Okay. And the second point is that we may require the shorter ion exchange column, because the affinity is higher, so the exchange capacity is also higher. So we find that we can use a smaller amount of ion exchange resins in comparison to the weak resins which are there. May require a shorter depth of the exchange column. And similarly, we can also apply a higher flow rate, because we are having a very high affinity towards the ions which are being replaced. So that's why we may find that the higher flow rates may be applied to the column. And similarly, but the one of the drawback that we are having is that we may require a very high regenerate concentration, because the affinity to the ions, so it is very high, so the resins, they are holding very tightly to the ions which basically have been replaced by the resins. So when we try to now remove these ions, so we may require a very high amount of regenerant in that case, so that we can replace the entire cations or anions which have been exchanged by the resins by ions of interest. For example, if we want to replace it by H plus ions or Na plus ions, then we have to apply a very high concentration of regenerant in comparison to resins which are having lower affinity. Okay. So this means that when we are having a strong acid resin or a strong base resin, so then it may require a high value of regeneration or high value of regenerant in comparison to the weak acid or base resins. So now we consider a very simple equation, that is R minus A plus, and which is the A plus ions are being replaced by B plus ions. That is, we are talking here of the ion exchange process which are involving two monovalent ions. So Anderson in 1975, so they discussed this process of ion exchange using the strong ionic resins. So this equation can be applicable to the strong ionic resins, and here we can see that the B plus ions are replacing the A plus ions. So the B plus ions are going on to the resin and A plus ions are going into the solution. Okay. So if we say that at the equilibrium conditions, so the fraction of the A plus ions which are present in the solution will be the concentration of A plus ions in the solution divided by the total ionic concentration in the solution. For example, here we are talking about the cations, so the total cationic concentration in the solution, and similarly the fraction of B which is present in the solution will be determined as B plus ions, the concentration of B plus ions present in the solution divided by the total cationic concentration in the solution. So if we take the fraction of A and fraction of B which are present in the solution, if we add these two things and if these two ions are only present, so then we can say that the fraction of A and fraction of B, we add these two things, then it is equal to 1. So here C is the total cationic or anionic concentration in the solution, whichever is we are interested. For example, in this case, we are talking about the cations. Now, similarly, when we are having a resin, so resins are having a plus ions. So A plus ions and B plus ions are there in the solution. So now this B plus ions are replacing A plus ions and A plus ions are going into the solution. So then what happens that at a certain point, this equilibrium happens, that is the rate of the replacement is equal to the rate at which it is going out of the resin. Right? So in that case, the equilibrium condition happens, and we find that the fraction of the A plus on the resin will be given by R minus A plus, that is the concentration of the A plus ions on the resin divided by C bar. Here C bar is the total ionic concentration present on the resin. For example, here we are having only two ions here, that is A plus ions and B plus ions. So it may also represent the total resin capacity in equivalents per liter. That's why we are talking about only two ions here, A plus ions and B plus ions, because A plus ions will also be present on the resin, and similarly some amount of B plus ions may also remain onto the resin at the equilibrium conditions. So we can say that the fraction of B plus ions present on the resin will be R minus B plus, that is the concentration of B plus ions on the resin divided by the total concentration of the ions on the resin. So now we can write down this equation, that is the selectivity coefficient. Here, for example, we can write down the selectivity coefficient for this equation as B plus ions. Here, this is not B plus only. Right? So we can say that the B plus being replacing the A plus ions. So selectivity coefficient for this can be written as A plus ions present in the solution into the B plus ions present on the resin divided by A plus ions present on the resin into the B plus ions present in the solution. So this equation we can write down as the selectivity coefficient, or we can say the equilibrium expression for the above reaction. So this reaction, or we can say this selectivity coefficient can be replaced as the fractions of the ions. For example, we can write down x bar B, that is representing our B plus ions present on the resin. Similarly, x A plus, that is the representing the fraction present on in the solution of A plus ions. Similarly, x bar A, that is the fraction of the A plus present on the resin, and B plus ions present in the solution. So now if we can write down the x A plus, for example, x A plus will be equal to 1 minus x B plus. Similarly, we can write down that x bar A plus will be equal to 1 minus x bar because these two fractions when we add they come equal to 1. Okay. So we can write down in this way, and if we replace the previous equation, that is the selectivity coefficient equation, so we get the equation like this, that is x bar b plus 1 minus divided by 1 minus x bar b plus into the selectivity coefficient into xb plus 1 minus xb. So this equation gives us or tells us that what fraction of the b plus will be there in the solution and what fraction of b plus will be there on the resin. So if we know these values, for example, we have already talked about these values in the previous slides, right? So these values can be taken for a specific set of conditions. So we will discuss this in a coming numerical. This equation is specifically applied for exchange between the monovalent ions. Okay. So now we can see that if we draw a curve of the monovalent ion, that is the concentration of a monovalent ion, let's say A plus here, which is present in the solution, and the concentration of monovalent ions present on the resin, that is X bar A plus and X A plus. So this distribution will depend upon the selectivity coefficient value. For example, you can see here that if the selectivity coefficient values are low, so in that case, the higher concentration of this A plus or higher fraction of A plus will remain in the solution. As you can see that the 0.1 selectivity coefficient, find that mostly it is present in the solution. Similarly, if the selectivity coefficient increases, the value increases, we find that the higher fraction of the A plus goes onto the resin. So these distribution curves can be used to assess the effectiveness of the resin for removal of a given ion based on the selectivity coefficient. So here, so x bar b represents the extent to which the resin can be converted to the B plus form, right? And similarly, x bar b also corresponds to the maximum extent of regeneration that can be achieved with a regenerant which is having a composition of xp. So suppose when we are talking of the regeneration process, it is possible that all the sites may not be replaced by the ions of the interest that we want to replace. Okay. So this x bar b will give you, or the fraction of b will give you the amount of regeneration that can happen when we are putting a regenerant which is having a composition of B plus ions. So this will also tell you that what is the maximum extent or what is the maximum percentage of the regeneration that can take place. It will also tell you about the regeneration efficiency of that particular resin in respect to the particular type of ion. So now we have seen that the equation was applicable for only monovalent ions. Now, so we can now write an equation between the monovalent ions and divalent ions on a fully ionized exchange resin. For example, we can write down the equation, for example, B2 plus, placing the A plus ions which are present on the resin. So this equation represents the exchange of B2 plus placing A plus ions. Okay. So this equation can be represented, and again we basically solve the selectivity coefficient for this equation. So we can get this type of equation here. For example, here x bar b2 plus, which is there, divided by 1 minus xb 2 plus bar, that is the fraction of the resins which are present, the b plus which is present on the resin. So this is the square term comes here because we are having a square term here, this case, right? And similarly, the selectivity coefficient for the reaction into C bar divided by C will come here, right? And similarly, the fraction which is remaining in the solution divided by the fraction which is there, which is not there in the solution, that is x minus 1 minus x b plus 2 plus here, and this whole square. So basically the two square term comes here. In that case, if we are replacing, we are having the equations where the divalent ions are replacing the monovalent ions. So in that case, this equation may be applicable for finding out the fraction of the ions in the solution and fraction of ions on the resin. Okay, so if we write a generalized equation, that is Bn plus replacing A plus ions or the monovalent ions, or N plus valency ions replacing the monovalent ions. So this equation can be written where basically we can see the resin fraction, the solution fraction, the resin fraction and the solution fraction. This is at the equilibrium what is happening, and this equation can be again solved by solving the selectivity coefficient values, and we can get the generalized equation where the N plus ions, N plus valency ions, they are replacing the monovalent ions. So here You can see that the N plus ions present on the resin, so it comes here, and here also this is the 1 minus the fraction of the ions which are present on the resin. And raised to power n, so you can see here that raised to power n basically comes here, and similarly this is the selectivity coefficient for n plus ions replacing monovalent ions, and C bar by C raised to power n minus 1. So we can see here, if we write down here 2, n is equal to 2, right? So it will become 1. So that's why basically we can see here in the previous equation, that is equation 2, you can see that is C bar by C, whereas in this case this is C bar by C raised to power n minus 1. So we can say the values, that is the fraction present in the solution and fraction which is not present in the solution raised to power n value. Okay, so this may be your assignment also, that you can solve the monovalent ions equation in the similar way that we have solved in the monovalent ions cases. So you can solve and you can get this derivation. Can be your one of the assignments. So now we go on to the regeneration of the resins. So when all the exchangeable H plus ions or OH minus ions in the cation exchange or anion exchange resins, so they get exchanged with the cations and anions of the interest, right, which are present in the raw water, then the ion exchange resins are said to be exhausted. Okay. So suppose we are having a resin which is laden with H plus ions and we are passing calcium through it. So once the initial concentration, that is the inlet concentration, becomes equal to the effluent concentration of the calcium, so then we say that cation exchange resins have been exhausted. So at that point of time, we try to regenerate it by using HCl or by using NaCl, the brine solution, or by using NaOH in case of the anion exchange resins, HCl and NaCl in case of the cation exchange resins. So these are the simple reactions that can happen, right? So here these reaction basically tells us how the regeneration is happening. That is, now the H plus ions, they are replacing the sodium ions, right? Whereas in dilute solution the opposite is the case, whereas in the regeneration the case is reversed. And similarly the OH minus ions basically they are replacing the chloride ions in case of the anion exchange resin. So that is how the regeneration happens, and we take strong solutions. For example, 8 to 10% of solution may be taken for HCl or NaCl or NaOH solution, so that we can regenerate the cation exchange resins or the anion exchange resin. So it also depends upon the type of the resin that we are talking about. If it is a very strong resin, then in that case we may increase the concentration of HCl, NaCl or NaOH. And if we are having the weak acid resins or weak base resins, in that case we can reduce the concentration of the our regenerant. So they are also known as the regenerant. So now regeneration of resins means that we return the resin to its initial exchange capacity. It is possible that we may take it back to the initial exchange capacity, or we may not be able to take it to the initial exchange capacity. So it depends upon, it tells us about regeneration efficiency. So if the complete regeneration has occurred, so this means that the number of equivalent of ions removed from the resin during the service period is equal to the number of ions which are exchanged during the service cycle. Okay. So this means that the complete regeneration has happened in that case, whereas the regeneration efficiency can be defined as the total equivalent of ions which are removed from the resin during the service period and total equivalent of ions present in the volume of the regenerant used. When we are doing the regeneration process, how many equivalent of ions are removed from the resins and how many total equivalent of ions which were basically subjected to the resin, so that tells us about the regeneration efficiency. So if the efficiency is low, so this means that we will require a high regenerant will be used, and it may also enhance the cost for the generation. And if we want to increase the level up to which the regeneration happens is also known as the regeneration level. So regeneration efficiency will be higher for the weak ionic resins because they have high affinity for H plus or OH minus ions, whereas when we are having strong acid resin or strong ionic resin, so in that case we can have the low affinity for H plus and OH minus ions, and that's why the regeneration efficiency is generally smaller. So the value of K, that is the value of the rate for the regeneration, is inversely proportional to the value for the initial reaction. For example, when we talk of the strong acid or base ion exchange resin, so in that case the initial reaction, the value, the rate of the initial reaction is quite high. So the rate of the regeneration will be smaller. So ion exchange regeneration technologies can have two type of applications. That is, we can have the co-current regeneration systems. We can have a counter current regeneration system. For example, when we are providing the service in one direction and we are providing the regeneration also in the same direction, so we say it is a co-current regeneration. Whereas the counter current regeneration system means that we apply the service in one direction, whereas we go for the regeneration in the opposite direction. So that is called the counter current regeneration system. And the counter current regeneration system has a definite advantage that it provides a better quality of water because it is having a low ionic leakage and it is having a higher chemical efficiency, and it is also basically it results in lesser amount of regenerant basically that is used, and it basically reduces the wastewater that is being generated from the ion exchange process. So let us talk about that what is the co-current regeneration system and what is the counter current regeneration system. So you can see here that the top figure that you see is the co-current regeneration system, in which the feed basically water is being put onto the resin, and this resin is a H plus resin, right? So here let's say the sodium ions basically are being removed by this resin. So we see that the initial phases will be covered by the sodium ions, and the lower phases here we can see that it will be the H plus ions, because the H plus ions will be replaced in the top layers by the Na plus ions, but it is possible that in the lower layers some of the H plus ions they remain here, right? So after the service cycle, that is the treated water is coming here, and when we stop the operation, that is the service cycle is stopped. So then we go for the backwashing. So backwashing is done so that we can expand the bed of the resin, so that if there are certain suspended particles, suspended impurities, so they will go out with the washing. So we go in the backward direction for the backwash, and after that we apply the regenerant and rinsing and regenerant in the same direction as we applied for the feed. That's why it is called co-current method, and we see that the top layers again will be replaced by the H plus ions, and it is possible that the sodium ions may not be replaced in the bottom layer. So as soon as we now start the service, we will see that the sodium ions in the bottom layer, which were remaining, right, which remained during the regeneration process, so they may start coming into the product water initially, and that is called the leakage of the ions. So you find that in the co-current system, we may have a higher leakage coming into the effluent water in the initial stages. Okay. Whereas in the countercurrent system, we go for feeding in one direction. For example, let's say we are feeding it here, the sodium ions are replacing the H plus ions, and we are getting the treated water here. So the H plus ions basically remains here, right? Sodium ions on the top. So now when we go for the regeneration in the opposite direction, so we find that now here everything is replaced by the H plus ions, right? And sodium may remain in the top layers, because if the regeneration efficiency is not high, so you may find that the sodium may remain in the top layers. But again, when we start servicing, so we find that the product water may not have any leakage. So no leakage basically is found in such type of system, and that's why we prefer more of the counter current regeneration. So here we have already discussed about the ion leakage, which happens for the co-current method and the counter current methods, right? And we see that the sodium ions, they may exit the column as leakage, yeah, as it is shown in the figure 4a, whereas there is no leakage which is happening in the counter current system, which is represented by figure 4b, and we see that the resin bed is predominantly in the regenerated form at the bottom of the vessel, and because of which a lesser leakage takes place in that system. So now when we use the counter current systems, we can reduce the chemical costs, right? Okay, we can improve the water quality, and we can have less waste volumes in comparison to the co-current system. Okay. So this means that the counter current system is more productive. It utilizes small vessels, and it may have faster regenerations to mechanical. So we stop here only, and these are the references that I have used for this lecture. And in the coming lecture, we'll talk about the applications of the ion exchange process in different type of wastewater systems or water systems, right? And we will also talk about certain numerical examples so that can clear whatever we discuss. Thank you.